We live in a classical world, which means most of the things that we see around are bound to follow Newton's maths. If you throw a ball at a solid wall, it hits the wall and then bounces back at you. If you throw that ball as a projectile, it will follow a particular trajectory before it falls. Using Newton's laws, one can accurately calculate the trajectory of that ball. However, laws of physics are different on a small scale. Particles like electron, proton, and neutron, which makes up an atom, behave very differently than anything that we see around us. They don't follow Newton's laws. They follow the rules of the quantum world. In our classical world, a ball has a definite position. It is precisely present there. But the same is not correct for an electron. There is a certain probability for an electron to be present at a particular point in space. So, there is some chance for an electron to be present here, some possibility that it is there. One cannot say with absolute certainty that it is at that point. One can only talk about its probability. Further, when you measure its position, its probability cloud is lost, and now it takes a definite point in space. Now, the electron is present at that point precisely. Thus, making a measurement makes an electron lose its probability halo and choose an exact location. But isn't that like throwing a dice? Before you throw a dice, there is a probability of getting any one of the possible numbers. After you throw the die, it will give you one particular number. Is the act of electron position measurement the same as that of a regular die? The answer is no. The weird thing about quantum objects like an electron is that before measurement, it is present at many places at the same time, like a ghost. And when you make a measurement, it bounces in one of the many positions. To see this spooky action in play, instead of position, let's understand the spin of an electron, which also shows the same ghostly properties. Electron spin is a quantum property of the electron, which can be measured in two directions, vertical and horizontal. After the measurement, there is a 50% chance of getting a spin up state and 50% chance of spin down state. Remember, electron spin has nothing to do with an electron spinning like a ball. Spin is the property of electron itself, just like the mass and charge of an electron. It's just that scientists are not good at naming things. Now, let's take two electrons and pass them through our machine. This machine creates a connection between these two electrons. Now we call these electrons to be entangled. In this state, when one electron is measured to have spin up, then the other electron measured in the same direction will have spin down. Measuring spins of two particles in the same direction, that the spins will always be opposite. So, let's consider an experiment with our two scientists, Alice and Bob, with each carrying an entangled particle. We take them hundreds of kilometers away. Now Alice measures her electron to be spin up in vertical direction. The moment she measures it, by the property of entangled particles, the other particle when measured in the vertical direction will always be in a spin down state. It seems like measuring the spin of one of the entangled particle has influenced the spin of the other particle. Spooky action at a distance. Well, not so fast. Let's consider the same experiment, but this time with a coin instead of electrons. Suppose that a coin is put into either Alice or Bob's bag, so that there is a 50% chance that it is in Alice's bag and also 50% chance that the coin is in Bob's bag. When they are far apart, Alice checks her bag and finds the coin. This immediately fixes that the coin is not in Bob's bag. Isn't this coin behaving like a quantum particle? Isn't the coin showing the same spooky action at a distance? The answer is no. In our electron experiment, suppose Bob always measures spin in vertical direction, and Alice can measure spin in both directions. If Alice measures the spin in vertical direction and found it to be spin up, Bob will find his electron to be always spin down. On the other hand, if Alice measures spin in horizontal direction, Bob will measure his electron spin to be spin up 50% of times and spin down 50% of times. It is this choice of measurement, horizontal or vertical, by Alice that affects the outcome of Bob's electron. In the case of coin, there was no such choice affecting the result of other partner. So coins are not quantum objects. The two entangled particles don't have spin up or spin down in the beginning. They were in a probability halo of up-down spin. Only when one of the spins is measured, their probability halo is lost, and the system takes a particular state. But what makes the quantum particle behave that way? For that, let's make a classical entanglement. Just as before, we have Alice and Bob, but now there is a central machine that throws identical balls towards Alice and Bob. The machine throws 4 types of balls: small red, small green, big red, and big green. Bob can only know the color of the ball and not size. Alice can know color and size, but only one at a time. If Alice measures the color of the ball and finds it red, then she knows that Bob's ball is red with 100% certainty. But if Alice measures the size, then there is a 50% chance for Bob to find the ball to be red. We can ask the same question again. How does the choice of measurement of Alice affecting the outcomes of Bob? Our classical entanglement experiment works only when our observers, Alice and Bob, have a limited knowledge of the system, either color or size, but not both. Now, since quantum particles behave the same way by quantum entanglement, does that mean our understanding of quantum world and quantum particles is limited? Is our knowledge of quantum world incomplete just as Alice and Bob can measure only size or color? This was Einstein's take on quantum physics. He stated that quantum physics is incomplete and one needs a different theory to explain this incompleteness. But in this case, Einstein seems to be wrong. If you want to know how, stay tuned and never stop questioning.